Hey, chemistry, it's Wednesday, May the 13th, and I am glad to see you guys again. We got one more week. You can see the light at the end of the tunnel. Hang in there. You're doing well. In fact, you're doing really good. In fact, really, really good. You know, your average on these lessons is 6.5 points higher than your average for the entire of the year that we've had so far. So you guys are really working at it, and I appreciate that. Okay, well, we did a titration with this burette and stopcock. This, of course, is a burette and a pinchcock. We haven't done that yet. That's just for display. But anyway, we use sodium hydroxide and hydrochloric acid. Sodium hydroxide is the primary ingredient in Drano, and it comes to me packaged in these little pellets. And then I have to dissolve them in water to the concentration that I want. And you guys know how to do molarity, so you could have taken some of that, dissolved it in a certain amount of water to get me 1/10 molar for this burette. And we titrated it, and I kind of overshot it. If you look at it, you can see it's still a little bit pink. And so what's going to happen here, let me go ahead and dump it into a beaker so it's a little bit easier to manage. And the question I have is, if I dip this hydrogen paper in there, should it be, since it was a strong acid, hydrochloric acid is called muriatic acid down at the store, Lowe's, and this is a strong base. So a strong acid titrating a strong base titrating a strong acid is going to give me a neutral, it's going to give me a neutral solution at the end there. But it's going to have a salt and water in there. So let me go ahead and test it with this hydrogen paper, universal pH paper. And you can see when you look on this thing, there we go, that paper is not red. So it's not an acid, not acidic. It is, in fact, neutral. You can't hardly see that, can you? Whoop, there we go. pH is 7. It might be a little bit towards the 8 since I overshot. Do you remember that? Instead of a light pink, it was a little bit darker lavender color when I did my titration. Now, the question I have is this, if it's neutral, going to give me an electrolyte? In other words, are there ions in solution? Well, let's check it. I guess there are, because what makes good electrolytes? Acids, bases, and salts. And that's a salt water right there. And so there are ions floating around in solution. In fact, what they are is sodium ions and chloride ions from hydrochloric acid. And those are what allows the electricity to flow through. Okay, that's nice. Let's go ahead now and do a problem on page 520. Turn to page 520, sample problem F. Okay, you ready? Right above sample problem F on 520, it says, use these 4 steps. Well, I use 3. Well, I guess balanced chemical equation would run it up to 4. So sample problem F says the titration is barium hydroxide. And hydroxide is -1 and barium is +2. And you can see that on your periodic table that barium is in group 2. And when you crissy-crossy, that's the formula. Of course, they said that in the problem, so that you shouldn't get that one wrong. It's added to hydrochloric acid. That's a strong base and a strong acid. Both of those are aqueous. I'm not going to write that in there because otherwise it clutters things up a little bit. And so what is it that are going to be our products? Do you have any idea? A salt and water. Yep, a salt. So it's going to be barium chloride. And barium is still +2. And chlorine is -1. When I crisscross, it's going to be a 2 right there. And what's the other product? The other product is water, H2O. But wait a minute, Mr. Schultz, you got 2 hydrogens and 1 more makes 3. Don't worry about it. When we use the coefficients, that'll balance things up nicely. So is this formula written correctly? Yeah. Is this formula? Yep. Is this formula? Yep. And that last formula for water is also written correctly. So all we have to do now is step 4. Imbalancing chemical equations. What's that mean? 1 barium, 1 barium. Do the oxygens last. That's always my suggestion. We got 1 chlorine, we got 2 chlorines. We got 2 hydrogens, and we got 2 hydrogens, making it 4. We only have 2. Now we're going to do the oxygens. We got 2 oxygens, and over here we got 2 oxygens. I think we got a nice balanced chemical equation. Okay, underneath barium hydroxide, write 27.4 milliliters. Okay, and 0.0154 molar. Okay, and then underneath hydrochloric acid, write 20 milliliters. And then put question mark molar. This concentration is what we're trying to figure out. Okay, what's the formula for molarity? Isn't it moles over liters? Okay, the molarity is 0.0154. Oh, we're gonna cross multiply. Okay, 0.0154 is molarity. The moles is what we do not know. Moles of what? Barium hydroxide. Where do you begin? You always begin with the reactant where you know 2 things. That's where you begin. And how many liters? Well, change that into liters by 3 bunny hops. 1, 2, 3 to the left. So it would be 0.027 liters. There's an invisible 1 under here, so the moles is going to equal that times that. We got my calculator. And I'm going to go ahead and do that. Calculator, here we go. 0.0154 times 0.027. 4.158 times 10 to the negative 4. 4.158 times 10 to the negative 4. That means 3 zeros. And a 4158. Negative 4 means there's 3 zeros, 4158. So we'll go ahead and do that. 0.0004158. Okay. Now, the next step. First, you look at the thing, the reactant that has 2 pieces of information, the volume and the molarity. And you calculate the number of moles and write it there on your equation where moles is supposed to go. And it always goes underneath because I told you to do it that way. Okay? And then over here, we're going to do stoichiometry to see how many moles would go under there. Well, isn't there a big 1 right here? 1 is to 2, as that is to what number? 1 is to 2 as that is to what number? Well, isn't X going to equal 2 times that? And you can do a simple proportion like this if you're simply going from moles to moles. Just go coefficient is to coefficient as moles is to moles. Now, some of you would just look at that and double this thing times 2. That won't change the power of 10, but it will change the number to be twice as big. So it's 0, 0, 0, 8316. That's 2 times that, because that's 2 times that. Okay, if that's the number of moles, then what is the definition of molarity, by the way? What's the definition of molarity? Well, isn't molarity equal to moles per liter? Okay, so molarity is what we're looking for this time. We're looking for the molarity of the hydrochloric acid. Moles of the hydrochloric acid is 0.000 8316. And the liters is 20 milliliters, 0.020 liters. Now we're going to take that and divide it by 0.020, and we're going to get 0.04158. That's the molarity of the hydrochloric acid. How did you get that? First, balanced chemical equation. Second, take the thing that has 2 pieces of information, the reactant, and calculate the moles. And then go ahead and do stoichiometry, compare moles with moles. You can use a simple proportion. And then you're going to use the definition of molarity again, except this time you're going to get the molarity. And the concentration of the hydrochloric acid is that. Let's see if we got it right on page 521. Well, looky there. 4.22 times 10 to the negative 2. That is this right here, see? 4.2 times 10 to the negative 2. Same thing. So that's all I'm going to say. I'm going to give you a couple of these problems to do. See ya.